used for the error control. Okay, for the error control. So this is a error control code. So that's why that code word consists the redundancy. Okay, so we use the redundancy. So are you understood that? I'm repeating again. This is very important concept. This is basically the concept that why we use the redundancy. Redundancy means that means the same message we are transmitting again. That means a code word possesses two messages or same messages, so that if one message is being distorted by the channel error or the channel noise, we can get our desired message through the redundancy. That means we are using the same message, another same message. So this is the thing. And this convolutional codes is basically designed so that the decoding can be performed in some structured and simplified way. That means when the coded messages are being received by the receiver, it can be decoded very simply and very faster way actually. So that's why we use the convolutional coding, the convolution arithmetic or convolution operation. So we will see later on that why this and how this convolution basically we do. So this is the thing that this is the encoder, and we are transmitting the segment of the messages. That means M1, M2, M3, M4, which segments, that means each segments consisting k number of bits, and at the output of the encoder, we have generated the encoded sequence. Mind it, this is encoded sequence. Okay, so this encoded sequence, each encoded sequence consists n number of bits. Okay, and as you know that n is greater than k. Now you can see that there is a term GF, that means Galois field. So what is the purpose of this Galois field? Okay, so this is nothing but this is a finite field. We know from our previous lecture of Galois field that Galois field is a finite field. That means this field consists of a finite number of elements. Okay, and this consists of a finite number of prime elements. Or when this is not prime, then we know that how to do this the arithmetics. So but here the Galois field is basically used to represent the bits. That means this is a finite bits, the source alphabet. Here it is written that the source alphabet is taken from a finite field of Galois field. That means GFQ, and Q is the number of elements. Okay, so just this is a representation, so you can understand with this example that GF3. So GF3, so this is the source alphabet at the encoder. Okay, source alphabet at the encoder. That means at the encoder input, these are the alphabets. Okay, at the first class I have told you that the alphabets, about the alphabets. So these alphabets actually, that means this total, that means the set of M1, M2, M3 and M4. That means you can say that here it is written M0, M1 and M2. So this is M1, so you can represent it also by M0, M1, M2, M3. So these are the alphabets. That means this M is the alphabet. M is the alphabet, or you can say the set of message, the total set of message. That means M1, M2, M3, M4. These representation is called the alphabet. That means M is the alphabet, which consists these 4 message segments. Okay, so this is the source alphabet of the encoder. So suppose we have taken GF3. That means we have taken 3 messages at the finite field, because Galois field is a finite field which consists the finite number of elements. So GF3, q equals to 3. That means there is a 3 message segments 0 to k. Each message segment consists k number of bits. So 0 to k, 0 to k, 0 to k. This is segment 1, 2 and 3. So these k elements of each segment are belongs to extended vector. So as I have told before that this is total called the vector space, and this is the vectors. Okay, these individual vectors, that is m1, m2, m3 and m4, these are the individual vectors, and this total set of vectors is called the vector space. And these k elements of each segment, that means each vector consisting k number of bits. There is a three messages, that means 3 segment, that means gf3, 3 segment, and each segment consists k number of bits. Okay, so that's why the extended vector, that means the total number of elements, the total number of message elements, that will be gf3 to the power k. So that's a representation. That's basically a representation. Okay, so this is a source alphabet. I'm repeating again, the source alphabet at the encoder. This is gf3 and this is m0, m1 and m2. These are the vectors. Each vectors are consisting individually k number of bits. So the extended vector, that means these k elements of each segment are belongs to the extended vector gf3 whole to the power k. Similarly, for this case, that means at the output of the encoder, I have told you that we have generated a encoded sequence. That means these are also segments. This is segment 1, segment 2, segment 3, sorry, segment 2 and segment 3. So these are the segments also, and each segment consisting n number of bit. Okay, so these 4 segments also defined in the Galois field. Okay, this 4 segment is also defined in the Galois field or finite field. This is basically a representation. Okay, we are considering gf3, that means there is a 3 message. If there is a 4, then it will be gf4 in this way. So for the three messages, we will get a encoded output. Suppose 3 output, or so that basically represented as gf3 to the power n. So this is the extended vector space for the output, as well as the extended vector space for the input is gf3 to the power k. Okay, so because message bits are represented by the k bit representations, and the encoded bit are being represented as n bit representation. Okay, so output of the encoder, you can see that this is 0, 1 to n, 0, 1 to n. So this is segment 1, segment 2, and in this case the encoded segments belongs to the extended vector space of gf3 to the power n. So for the output of the encoder, this is represented as gf3 to the power n. That means this is the total possible number of encoded sequence, and these basically the total number of possible messages. Okay, messages. So these are the concept. This is basically the concept. So we can see that from the next page, that gf3 to the power k is basically defined as message vector space, the total vector space. Okay, and gf3 to the power n, we are basically taking 3, but generally this is represented as gfq. So you can say that in the general form, GFQ,